Welcome to section 8.2. We're talking about the magnetic force on a charge. You need to know that the magnetic field strength is measured in the Tesla, which we short form with the capital letter T. And note that 1 Tesla is equal to 1 kilogram per coulomb second. It should be interesting to know that the magnetic field strength near Earth's surface is approximately 50 times 10 to the negative 5 Teslas. And why am I mentioning this whatsoever? Well, here's the reason why. An MRI has a field strength of 7 Teslas. When we're looking at calculating the magnetic field strength, we know that the magnetic force, or I'm telling you that the magnetic force is equal to QVB sine theta. And we're defining a few new variables in this case. Fm is the force on a moving charge measured in newtons. Q is the charge on a particle measured in coulombs. V is the magnitude of the velocity of the particle in meters per second. B is our magnetic field strength, in Teslas, and theta is the angle between the velocity and the magnetic field strength in degrees. Note, because we're dealing with force, magnetic force is a vector quantity. But the above equation only calculates magnitude. Of that magnetic force. So similar to the reading that I had you guys do yesterday as a short introduction, we need to know how to determine that direction of the magnetic force. And similar to the right-hand rule for straight conductors and solenoids, we also have a right-hand rule for a moving charge in a magnetic field. And here's what you need to know for the most part. Your right thumb points in the direction of the velocity. Straight fingers, and this is in your right hand still, point in the direction of the magnetic field. So right thumb points in the direction of the velocity, straight fingers point in the direction of the magnetic field. The palm of your hand will point in the direction of the magnetic field. Something to note that what I've just written here, the right hand rule, this is for a positive charge. For a negative charge, still use the right hand rule, but use the opposite direction that your palm is facing. So we'll use the opposite direction of the palm of your hand that it is facing. We'll give you the direction for the negative charge. So let us see a combination of both of these used in an actual example. Where you have a proton, where it's positive charge, so we don't need to worry too much, and it's moving horizontally 8.9 times 10 to the fourth meters per second north, entering a magnetic field of strength 1.4 Teslas. And this field is directed vertically upwards. Calculate the magnitude and direction of the force of the proton and determine the gravitational force of the proton. And let us determine the ratio of the gravitational force to the magnetic field on the proton. So let us work with A first. And because this is moving horizontally at 8.9 times 10 to the 4 meters per second north, we're going to change our thinking for a second and think about pointing to the right is in the north direction for now, just because of this horizontally and north, okay? Just a little different to wrap our heads around. Let's think about the direction that this force is first going in. So let us consider this case. We have some type of magnet happening, and we have our velocity heading in the northerly direction as such. And this is where I'm going to try my very best to show you the right hand rule as it works the best. And do bear with me. So I have my velocity going in the north direction towards the right horizontally, and I have my field directing vertically upwards. That is where my field is going. So if you can see my thumb, it's pointing towards the right, similar to how my velocity is in this case. And our field straight fingers are facing forward, or vertically upwards in this case, as given in the question. Which direction is our magnetic force going? And you see my palm of my hand is facing towards the screen right now, but it's coming out of the page. So therefore, to describe the direction of my magnitude force, or the magnetic force, is coming out of the page. So I'm just going to leave that as a note right now. Force is out of the page. Given in this question as well, so we're going to go to the actual magnitude now. Remember, charge of a proton, 1.6 times 10 to the negative 19 coulombs. The speed in this case is 8.9 times 10 to the 4 meters per second. I have a field strength of 1.4 Tesla. And let us also look at what the angle is between my speed and magnetic field. We can see very clearly that they're at a 90-degree angle in this case. So let us calculate Fm. Fm is very easy. We calculate the magnitude now, making our substitutions. Hopefully I have enough room. Sine 90 degrees. Substituting that all into a calculator, you get 1.99 times 10 to the negative 14 newtons. Look for significant digits. We need only 2. So 2.0 times 10 to the negative 14 newtons. And because of that little right-hand rule, thumb points in the direction of the speed of the particle, or velocity I should say, straight fingers to the magnetic field, we see our force is coming out of the page towards the screen in this case. And really, these types of questions can be done exactly the same, even if we have our angle between V and B, say, on a 45-degree angle. You're still able to calculate or determine the direction of the magnetic field. Which direction would our velocity be going in? You see my thumb pointing it in that direction. It could point in the other direction as well, depending on which direction, or if it's positive or negative charge. If it's a positive charge, it points out of the page. If we have a negative charge, think about which direction that's going to go. Opposite of my palm, it would go towards the page. A little bit of a tangent there. Let's go to part B, where we are determining the gravitational force of the proton. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. We can very easily calculate that gravitational force now. Gravitational force, Fg, will be the mass of the proton multiplied by g. So we'll have 1.67 times 10 to the negative 27 times 9.81, which is 1.638 times 10 to the negative 26. Again, two significant digits. And there we are. Then our last question has, let's calculate the ratio in part C. Well, that's very simply going to be Fg over the magnetic force. So we'll take 1.6 times 10 to the negative 26. It's a ratio, so we'll divide it. And that will be over 2.0 times 10 to the negative 14, which we end up getting 8 times 10 to the negative 13 to 1 as being our ratio of the gravitational force to the magnetic force. And that's everything for today. I'm hoping that that makes sense. Do make sure you practice that right-hand rule for the magnetic